Professor Bialas here. In this video we are going to be talking about section 10.3 where we simplify radicals. They also throw in what's called the distance and midpoint formula. We'll end with that. But the main idea here is simplifying radicals. If you cannot simplify radicals, adding, subtracting, multiplying, dividing, rationalizing denominators, all that stuff is going to be pretty much impossible. This is the foundation for everything we are going to be doing throughout the rest of this chapter. Okay, so before we get into actually simplifying them, we are going to look at a couple of rules that we need to know in order to carry out that simplifying procedure. So let's start off with those rules. First rule is the product rule for radicals, which states if I have an nth root of a, some kind of radicand, times the nth root of b. Notice those indices are the same. They have to be the same. Then all I would do is take that nth root of the product. So basically, if I'm multiplying two radicals with the same index, I can simply convert that to multiplying those radicands. Nothing more than that. Same thing would go with the quotient rule. The quotient rule starts with nth root of a over the nth root of b. So we're dividing two radicals would be the same as that radical of the quotient itself. Okay. Now remember, when you have an equal sign like this, we have that symmetrical property that allows us to reverse that equal sign. So what that means is, not only can we take these two radicals and pull them together as one, but we can also take a radical of a product and break it up into two separate radicals. That's what we're really going to be doing when we get into the simplifying aspect of radicals. Same thing here. A lot of times we're going to start with a fraction under that radical that we can't really do much with, but then after we break it up, we can work with them individually. Okay? So let's start off by just doing some products, see how this product rule works, go into some quotients, and then we'll get into the actual simplifying. So let's start out with something like this. Again, I'm just going to ask you to multiply. And let's say we have the cube root of 7 times the cube root of 2. Since those indices match, they're both cube roots, all we need to do is take 7 times 2. That gives us a 14, but we need to keep that cube root. It's as simple as that. Okay? Yes, we're multiplying radicals, but we're just multiplying 7 times a 2. End of story. Okay? Let's do one more. How about something like that? Okay. Now, you may look at that and say, well, I'm going to need this quotient rule here. Not quite yet. Okay. In this case, we just have two fractions being multiplied. Let's multiply through. So we are going to have the square root of 3 times y, and then x times 2, or just 2x. We're going to do a little bit more with that in the next couple sections when we talk about rationalizing denominators, but for this point in the game, that's perfectly fine to leave it as is. Okay? Let's look at a couple more. Okay, now I'm not just going to be multiplying. I'm going to ask you to simplify with the quotient rule. And let's say we have something like this. Okay, now, remember, we have the option to either keep these two separate or to pull them together as one. Typically, when they're together as one, that's going to be beneficial to us if that fraction is reducible as a normal fraction. If that was, let's say, 9 over 36, I would just want to keep that together as one fraction and reduce the fraction. But if that's not happening, like here, then it would be more beneficial to us to keep these as separate radicals. So what I'm going to do is think of this as the square root of 9 and then the square root of 25. Square root of 9 is 3, square root of 25 is 5. And that's all there is to it. Okay? Again, what it allows us to do is either take it apart, or if we started like this, we could pull it together if that would help in the problem. How about something like this? Okay? Again, y over 36 we can't really do much with. But if we separate that into square root of y over square root of 36, that doesn't come out as neatly as the previous example, but square root of y over 6. And we at least get rid of that radical in the denominator. Okay? That's pretty much what that product rule and quotient rule, just at the very surface of it, that's what they're going to be used for. Okay? Now, let's bridge into actually simplifying radicals. So let's start out, I'm going to say simplify. That's it. Okay. Now, if I start out with something nice, let's say square root of 49. Square root of 49 can very easily be simplified by simply taking the square root. Square root of 49 is 7, done. End of story. Now what happens if it doesn't work out so neatly? Let's say we have square root of 18. Okay, now square root of 18 doesn't come out nicely. But what we can do is break it down into smaller numerical components. And that's where the simplifying aspect comes from. Now, the thing that I want you to look for here, you may have seen different methods of doing this in the past. A popular one I remember seeing was jailbreak method, where you do prime factorizations and you look for pairs of numbers or groups of threes of numbers and pull them out. That's a perfectly fine method. However, if the number gets large, it can get very cumbersome. So what I like to do instead is to think to myself, what number that is a perfect square divides 18 evenly? Okay. Now, if you're a little shaky with your perfect squares, I said in a previous video, make that list. If I have n is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, square them. 1 squared, 2 squared, 3 squared, 4, and so on. Get to know those perfect squares. That doesn't mean you have to have them all memorized. And honestly, I would probably go out to 20 on that list. You don't have to have them all memorized, but at least become familiar with them. So that if you see a number, you may not remember exactly what the square root is, but you know something special about it. So again, 18, I'm not looking to see what divides an 18. I'm looking to see what perfect square divides an 18. 1, that's always going to be divisible, but only use that if that's the only option you got. 4, does 4 go into 18? No. How about 9? Yes. Okay. 18 is also divisible by, let's say, 6. But 6 isn't going to help us because it's not a perfect square. So let's go with the 9. So 18 can be thought of as a 9 times 2. Now, look at what I just created. I factored the 18 to 9 times 2. But now I also created a situation where I can use that product rule. So instead of square root of 9 times 2, I can think of square root of 9 times the square root of 2. Square root of 9 being 3, and square root of 2 stays put. Okay? What I did was I took out the nice even square root portion of that value, and instead of square root of 18, now I just have to work with a square root of 2. Okay, that's what it means to simplify a radical. Again, with the 18, this isn't like with factoring where we were looking for, okay, does 1 go into it, does 2 go into it, does 3 go into it? I'm just looking at these perfect squares. That is it. Okay, that's the only thing that I'm going to concern myself with. So, let's look at a few more of these. let's go to square root of, let's say, 50. Okay, let's stick with the square roots for a second. Now, again, what you're looking for is a perfect square that goes into 50. 5 goes into 50, but that's not going to help me. Okay, if I did, let's say, 5 times 10, and I broke that up like so, is that going to allow me to take any nice perfect square out? No. This isn't wrong, but it's not helping me in any way. So I'm going to dig in a little bit more. I'm only going to concern myself with these numbers up here. 1 doesn't really do much for me. 4 doesn't go in. 9 doesn't. 16 doesn't. 25 does. So I'm going to say 25 times 2. That's the same thing as 50. And now I can simply take that out as square root of 25 times the square root of 2. So 5 square root of 2. And that's all there is to it. Okay? Just again, focus on this list up here. Nothing more than that. What if I go with a cube root? Let's say cube root of 40. Okay? Now, in this case, since it's a cube root, I don't really care about these. I'm now going to jump to the perfect cubes. Again, make another list with those perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. Okay, and we can keep going. I would probably take that out to 10. There's really no need to go any further than that. You can go as far out as you want, but typically the numbers we use will be below that 10 cubed. Okay, so let's look at that 40. Okay, does 8 go into 40? Yes. So when we look at this, I'm going to think of this as 8 times 5. Okay, now I think of the cube root of 8, which is 2, and then cube root of 5 stays. Don't forget that index of 3. And there we go. Okay, so it's a lot like the guess and check with factoring, only the only difference is we're only looking at these. I'm not looking if 2 goes into it, and 3, and 4, and 5. Not that those are illegitimate numbers, but they're not going to help us in this situation here. Okay? How about this? Okay? Now, notice the index in this case is 4. So we're looking for 4th roots. So I don't have that list up here, but let's think about it. 1 to the 4th is just a 1. If I go 2 to the 4th, 2 to the 4th is simply going to be this 8 times another 2. That's a 16. Okay, does 16 go into 162? No. How would I go with 3 to the 4th? All that is 27, which was 3 times 3 times 3, times another 3. 27 times 3 is 81. Does 81 go into 162? Yes. Okay, so what I have is a 4th root of 81 times 2. And what did I raise to the 4th power to get the 81? A 3. And there's my answer. Okay? Again, these lists are very, very helpful because then you have all those numbers staring you in the face. But if you don't have those lists, okay, that, let's say on the test or something like that, you don't have that list in front of you, then just, this will take a minute to do, and then you can very easily fill in the gaps later on. Okay? So, let's go on to some variables now. Let's start with something that we know how to do. Let's say we have square root of x to the 6th y squared. Okay? Now in the past we had to worry if we were dealing with any real number or just positive real numbers. In this section, you're just dealing with positive real numbers, so you don't have to worry about those absolute value bars. So what we do here, what we did in the past, is we simply divided by that index. In this case, that index is understood to be 2. So 6 divided by 2 is a 3, and then 2 divided by 2 is just a 1. That's all there is to it. Okay? Now, what if those things didn't divide so nicely? Let's say we had square root of x to the 5th, y to the 7th. Those aren't divisible by 2 anymore. Okay? So how are we going to handle that? Now, it's all going to come down to that division using remainders when it doesn't divide nicely. So again, my index is 2. So normally I would take a 2 and go into 5. 2 goes into 5 twice. 2 times 2 is 4, with a remainder of 1. Then the 7. 2 going into 7. Whoops. Just division bar here. 2 goes into 7 3 times. 3 times 2 is 6. Subtract, and we have a remainder of 1. Now watch how I'm going to do this. Okay? I am going to get some x's and y's on the outside, but then I'm also going to have some x's and y's remaining in the radical. I say it like that as a little bit of a hint. Okay? So, when I was dividing this 5, I had 2 remainder 1. So what I'm going to write is a 2 remainder 1. The 1 remains in the radical. When I had the 7 divided by 2, I had 3 remainder 1. So 3 remainder 1. That's all there is to simplifying these variable expressions with radicals. Okay? When it comes out nicely, there was nothing remaining in a radical here. These would have 0 remainders, so there's nothing remaining. Here, there was something remaining, so we keep it inside. Those 1s don't have to be there, but again, as you're getting used to it, if you want to write them, there's no problem with that at all. Okay? Let's look at a few more. Let's go with a cube root of x to the 6th, y to the, let's say, 14th, z to the 7th. Let's say that. Okay? Now, if you can do the division in your head, more power to you, that's great. But if not, again, it takes a few seconds, it's worth writing it down. So I'm going to go with 3 going into 6, 3 going into 14, and 3 going into 7. Okay, let's write them out, and if there's a remainder, put R and then the number. So 3 goes into 6 twice, 2 times 3 is 6, and then if you want, you could put a remainder of 0, or you could just leave that off. 3 goes into 14 4 times. 4 times 3 is 12, and we get a 2, so we have a remainder of 2. 3 goes into 7 twice. 2 times 3 is 6. We have a remainder of 1. Okay? Now watch how this is going to be built. I like to just lay out all the possibilities so I have some place to go if needed. So watch what I mean by that. I may have some x's, y's, and z's on the outside. And I may also have x's, y's, and z's on the inside. Okay? I want to write them all out, so I just have to deal with numbers at this point. So for that x, I had a 6 divided by 3. So that's 2 remainder 0. So I have 2 with nothing remaining. And then I just erase that x. No big deal. For the 3 and the 14, that was with the y's. So I had 4 remainder 2. And then for the z's, I had 2 remainder 1. I could just leave it like that. And then, that's it. You may want, if this gets a little, kind of spread out because you're erasing a bunch of variables, you might want to rewrite it to make it look a little nicer. But this is it. That's all you have to do. Okay? Again, I like writing that x in there and then erasing it so I can just worry about where the numbers are going to be placed. No more than that. Okay? Now let's pull together those numbers and variables in one shot. let's say we have this. Okay, so square root of 81y to the 5th. Take the numbers first, then worry about the variable part of it. So square root of 81 is simply a 9. That comes out very nicely, don't have to worry about it. How about that y to the 5th? So again, if you need, you can do that division. 2 goes into 5 twice, so you got a 4 remainder, and then a remainder of 1 at the end of it. So with the y, you had 2 remainder 1. And there's your final answer. Okay, so get on. Okay, so again, let's start with that 24. I'm looking for a perfect cube that goes into 24. If I look at my list, I'll hit that 8 right away. So 24, I'm going to think of as 8 times 3. Okay, so what I do is I start, let me actually go underneath it here, by pulling out that 8 as a 2, because the cube root of 8 is 2. So I'm taking the cube root, pulling it out. That cube root of 3 doesn't come out nicely, so I am going to leave that underneath. So that just stays within the radical. Okay? And drawing arrows like that, if that helps, go for it. That'll help you map out where you're going with your material. Now with the A's and B's, again, I'm going to go with, it could be on the outside, it could be on the inside. Let's see what happens with that. Okay, if you need to write out the division, go for it. Or 3 goes into 8 twice with 2 left over. Okay, because 3 times 2 is 6. 8 minus 6 gives you that leftover remainder of 2. 3 goes into 4 once with a remainder of 1. Again, at this point, try to get out of the habit of putting those ones, but if you need to, don't be afraid to do so. And there you have it. Okay, so again, the variable exponents really just come down to simple division. Remainder stays inside or remains inside. The actual quotient comes on the outside. How about something like this? Now this is going to go bring back that whole quotient rule idea we had before. Now remember what I said, when it's separated like this, that's perfectly fine unless those two parts of the fraction are reducible. When they're reducible, it's going to be a little bit better for us to pull it together. 48 over 3, if those radicals are out of there, 48 over 3 is a nice reducible fraction. So I'm going to convert this into a single fraction because now I can work with it like normal. 48 divided by 3 is simply 16. Okay, 48 over 3, you could say 16 over 1, but 16 is fine. And then finally, square root of 16 is a nice 4. You may think to yourself, well, you didn't really reduce anything, you just carried it out. That is reducing. Okay, that whole like a 3 square root of 2, that happens when it doesn't work out nicely. But even when it works out nicely, that's considered simplifying or reducing a radical. Okay? How about this? Okay. Now, this one has a little bit more to it because you got the 3 on the outside down here. So we can't necessarily rewrite this nicely, but I want you to consider these two as one big radical. Okay? And as such, they can be simplified like a normal fraction. So what I'm going to do is start off by simplifying 80 and 5. So a 5 goes into 5 once, so I could just have a 1 there. 80 divided by 5 is what? Now again, if you can do that in your head, great. If not, don't be afraid to do this. 5 goes into 8 once. And then you got 6. So you've got a 16. Don't be afraid of that. Okay, that's how we get better. Now, what we end up with is the square root of 16y over 3, because square root of 1 is just a 1. 3 times 1 is just a 3. So by doing that simplifying, we essentially eliminated the radical in that denominator. Now we're left with this. So we have to simplify. Okay, so square root of 16 comes out nicely as a 4, but then square root of y, there's no exponent there to divide and get a remainder. That's it. It's just square root of y. And this is our final answer. Okay, so again, the rule of thumb is if you have a radical on the top and a radical on the bottom, those radicands that are underneath can be simplified like a normal fraction, as long as they're both in the radical, because of this quotient rule right here. Okay. Okay, how about this? Now, first thing we're going to do, since these are both cube roots, I can just treat these like normal numerator, denominator, try to reduce. Okay, so let's see if this works out. Now, the only thing that's going to go into a 3 is a 3. Does 3 go into 162? 1 plus 6 is 7, 7 plus 2 is 9. 3 goes into 9, so 3 goes into 162. So what we're going to do first is simplify as a normal fraction this 3 and this 162. Again, if you have to, 3 goes into 16 5 times, you've got a 15. 3 goes into 12 4 times, you've got a 12. So you have a nice clean 54 right here. The x is also reduced as normal numerator denominator. I got 2 of them gone, 6 of them left. So now let's clean up what we have. We still have that 5. We still have a cube root of 54, x to the 6th. And notice everything is out of that denominator. That's all we have left. There's no more fraction to worry about. But we still have that radical that we can try to simplify. So let's start with that. 54, if I look for a perfect cube, I would say that's 27 times 2. Okay? Now watch how this comes out. This 5 right here stays on the outside. This 27, after we take the cube root, would come out as a 3. And then this 2, I can't take the cube root of that, so that would stay as the cube root of 2. Okay, so again, 5 was just hanging out in the front. Cube root of 27, because it's still underneath here, is a 3. And then cube root of 2 doesn't come out nicely, so we leave it inside. Now, with this, remember it's 6 divided by 3. That divides evenly. There shouldn't be anything remaining inside. 6 divided by 3 is 2, so x squared on the outside. Okay? And then to clean it up, 5 times 3 is 15. X squared, cube root of 2. What we're doing here is a little bit of factoring when we do something like that, and then it's all good bookkeeping. Again, just be careful and make sure you follow where things go throughout the problem. The reason we're doing this is because then we have the cube roots still over those. We can take the cube root of 27 nicely. We can pull that out, and now instead of a 54 under there, we just have a 2. Okay, and when we get into adding and subtracting in the next section, what that will allow us to do is make radicals that don't look anything alike, make them actually match, and then they can go together. Okay? Let's do one more like this. Okay. Now there is a lot going on in this problem. Again, take it a piece at a time. First of all, since these are both fourth roots, that's a good thing. We can work with those fractions just as normal fractions. We don't have to deal with the radicals just yet. So what I would do here is I would try to clean up these variables because clearly there's something going on that can be reduced or simplified down. Now, the y's, there's 6 versus 1, so 1's gone, 5 is left. Okay, now this -3, remember what we do with negative exponents. They don't do battle. What we do is we switch the side that it's on. So this is going to come up to the numerator. Now when I do that, notice the denominator is completely empty. So what I have is simply a numerator of 3 times a fourth root of 243, x to the 12th, y to the 5th. Okay, now that x to the 12th, where's that coming from? Again, this -3 comes up, so I have an x cubed up here now, and then I add exponents, x to the 9th times x to the 3rd, 3 plus 9 is 12. Okay, so this is the expression I'm left with after I simply do regular polynomial type of exponent rules. Okay, now I need to reduce that. So this 243, I want to think of a perfect fourth power that goes into 243. If I dealt with 2 to the 4th, I don't have it written here, but what would that be? 2 to the 4th would be 16. 16 going into this doesn't work. 3 to the 4th, 27 times 3 is 81. 81 going into 243? Yes. 243 can be thought of as 81 times 3. Okay? Now again, how does this all fall out? This 3 right here just comes straight down. These are under the fourth root. So take the fourth root when you can. The fourth root of 81 is a 3. And then this standalone 3 stays as the fourth root of 3. We can't carry that out, okay, because it doesn't come out nicely. It's possible, but it doesn't come out nicely. Okay, so this just drops right down there. Now, what about the x's and y's? 12 divided by 4, that will come out nicely. 12 divided by 4 is simply a 3. 5 divided by 4 does not come out nicely. So I know there's going to be some y's on the outside, some y's on the inside. 4 goes into 5 once with 1 left over. Okay, or a remainder of 1. If you need to see that, show that division. There's nothing wrong with that. And now after that, we're just going to clean this up. So what we have is 3 times 3 is 9. X cubed y, and then the fourth root of 3y. Make sure your index doesn't float over and become the exponent on the y. So just write that clearly so you can tell the difference between an exponent and an index. Again, this 3 comes down. After I broke this up into 81 times 3, the fourth root of 81 is a 3, and this 3 stays inside. Okay? So again, there's a lot going on in these problems, but it's nothing that you haven't done before. We factored, we're just taking nice clean fourth roots, third roots, square roots, fifth roots, any of those roots. Taking nice clean roots. That's why we're picking nice clean numbers. And then we're doing very basic division to mess with those exponents on variables. It's as simple as that. Okay? Now I don't want you to beat yourself up if this is kind of, making your head spin a little bit, okay? Because there is a lot of moving parts. There are a lot of moving parts to this process, but I don't want you to think that this is something beyond you because it's some weird, complicated thing. Just remember, these are ideas and concepts we've done from the past. Once you see it and believe it, it becomes a lot more manageable. Let's finish this section up by talking about distance and midpoint formula. Okay. Now the hardest part about this is knowing the formulas. After that, the formulas are very, very easy to work out. So, let's start with distance formula. Now, what the distance formula is used for is, let's say we have 2 points, and I'm talking about points on a coordinate grid that have ordered pairs x1, y1 and x2, y2. Okay? I want to find the distance between those 2 points. Okay? Now, I don't want to just take a ruler out and measure. I want to be able to calculate that distance. Now, what I do is I don't just follow this straight line path. Let's say this is your house and this is, JJC's campus on a map. You don't just fly right there. Okay, we have to follow the roads. And if you look at a typical map of roads, you have basically a coordinate grid. So what we're going to do is follow the grid lines. We are going to go this way and then this way. Now when I did that, what did I create? I created a right triangle, didn't I? So, how can I use that? This right here is a horizontal measure that can be calculated by simply taking the difference in those x's. Okay? If let's say I'm going from an x-coordinate of 3 to an x-coordinate of 5, 5 minus 3 would give me a horizontal distance of 2. Same thing would happen with that vertical, it's just there I'm measuring the y-coordinate change. And that would be y2 minus y1. Okay? Now, how do we pull all of this together? Remember, with any and all right triangles, we have that good old Pythagorean theorem to fall back on. Your Pythagorean theorem is your c squared equals a squared plus b squared. Okay? In this case, the c is not called c. Your c is always the hypotenuse, but we're specifically looking at the hypotenuse as that distance we were originally seeking to find. So instead of c squared, I'm going to say that it's distance squared. Okay? Now, these sides, it doesn't matter which is a, which is b. I'm going to start with the x's, then go to the y's. So this one side, instead of calling it a squared, I can call it x2 minus x1 squared. Okay? And then the b would be y2 minus y1 squared. All I did was take these more specific expressions and plug them into the general Pythagorean theorem. Now, I'm looking for an equation that gives me the distance. So in that case, I want to have distance equals something. So all I need to do is take the square root. And when I take the square root of d squared, I get a nice, clean distance staring me in the face at the end. And then the other side is simply going to be the square root of this mess over here. This is the distance formula you need to know. And all that is a play on the Pythagorean theorem. Nothing more than that. Okay. When I was learning this years ago, I remember I had a problem. I always wanted to switch. I wanted to put plus, then minus, then plus. I would always mix those up. What helped me through that is, again, knowing this is Pythagorean theorem. So it's something squared plus something squared. A squared plus b squared. So plus goes in the middle, and then put the negatives on the inside. Okay? Let's just do one quick example of this to see how this plays out. Let's say I want to find the distance between these 2 points. Okay, and that's typically how it's going to be. Find the distance between these 2 points. So, as always, when you're using a formula, write it down. So I'm going to be using distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay? The x2 simply means the x-coordinate from the second point. x1 is the x-coordinate from the first point. Same thing with the y's. So what I get, x sub 2 is negative 2, automatically a minus because that's part of the formula. And then the first x-coordinate is a negative 1. I'm going to square that. Second y-coordinate is a 6 minus the first y-coordinate, is a 3. Be very careful plugging that in, because if you make a silly little mistake there, all the other algebra and arithmetic is going to be wasted. Okay, so look that over before you move forward. Now, what I then do, clean that up. I like to just calculate inside. Negative 2 plus 1 is negative 1. 6 minus 3 is 3. And we're here. Negative 1 squared is 1. 3 squared is 9. And then simply 1 plus 9 is 10. Now, if you ended up with like square root of 20 or square root of 12, simplify that radical down. Okay, but in this case, square root of 10, that's as good as it gets. The only other thing you could possibly do is plug that in the calculator and get a decimal approximation. Okay, but unless they specifically ask you to do that, exact answers are always going to be better. Okay, because once you start approximating and rounding, your answer is going to be a little off from there on out. Okay, that's distance formula. Nothing more to it than that. The hardest part, again, is knowing the formula. After that, it's just plug and chug, and you move forward nicely. Let's finish up with the midpoint formula. Now, midpoint formula is going to start with the exact same scenario with 2 points, except we're not looking at the distance anymore. We're going to be looking for the point that falls smack dab in between, called M, hence the midpoint. Okay, so let me change this here. Now, in order to do that, we're not going to create a normal looking equation. What we're going to do instead is build a model to find a new ordered pair, because we're looking for a point. Okay, now the model that we're going to have is x1 plus x2 over 2 and y1 plus y2 over 2. Okay, so we take the x-coordinates, add them up, divide by 2. Take the y-coordinates, add them up, divide by 2. Why the heck are we doing that? Distance formula, we did that because of the Pythagorean theorem. Why are we doing it like this here? We're doing it like that because what we're finding are the average of the x and the average of the y. When we average things, we add up what we have and then divide by how many there are. There's always 2 endpoints, so that's why the 2 is locked in stone. Then we're just adding the coordinates appropriately, because horizontally we would go average of the x's, vertically average of the y's, and that hits the midpoint in between. Okay? So again, don't try to just memorize x1 plus x2 over 2, y1 plus y. Average the x's, average the y's. If we know what average means, which we should at this point, then piece of cake. Okay, let's take those same 2 points that we had over here And let's try and find the midpoint. So I'm going to take the x-coordinates, -1 plus -2 over 2, and then 3 plus 6 over 2. And now I just have to simplify that as much as I can. In this case, -1 minus 2 is -3. I can't do anything else with that. And then 3 plus 6 is 9. And we're good to go. Okay, if you can simplify those fractions, please do so. But in this case, that's it. There's your midpoint. Okay, so distance formula, you got to have down. Midpoint formula, you got to have down. Okay, but if you know where they're coming from, it's a lot easier to see how that structure of the formula itself comes to be. Okay, so take your time with this. Please pay attention to the detail and make sure you map out your work nicely and cleanly so you can follow along. As always, keep working hard. Let me know if you have any questions, and I'll see you next time.